Hello everybody, welcome to chapter 1.6. Today what we're going to be discussing are shifting, reflecting, and stretching of graphs, how to identify that, and how to write equations given that information. So let's begin. We're going to use vertical and horizontal shifts to sketch graphs, we're going to use reflections to sketch graphs, and we're going to learn how to use stretches or shrinks to sketch graphs and functions. So let's begin. I already wrote out a little bit here, sorry, I got carried away. First let's talk about horizontal and vertical shifts. So to begin, it's important to know that if you have your function is the original, the parent function, and then it has a plus a c value, what that means is that it shifts up. If your function is the parent function minus a constant, that means your graph is going to shift down vertically. If your function is the parent function with a minus c inside the parentheses, inside next to c, then that means your graph is going to shift to the right. If it's of f of x plus c, still inside the parentheses, it's going to go to the left. And I recognize here that these two are kind of counterintuitive. Normally when we think about shifting to the left or to the right, negative means left and positive means right. However, what you need to think about is just the opposite thing. Understand that when it's inside the parentheses, you move the opposite way. You kind of move counterintuitively. And where we get that from would be setting that factor equal to 0 and solving. And so we get the opposite value for c every time. So just give yourself a little note. Opposite direction when inside. So when it's inside parentheses, it goes the opposite direction. Alright. For example, if we have the function f of x equals x squared plus 2, there's something we can identify here. We talked last video about those common graphs we should all know. What we can recognize here is that there's the function f of x equals x squared hiding in here. And what's happening to this x squared, to that classic parabola shape, is that we have a plus 2. So we can understand then that this is going to be f of x squared shifted upwards by 2. And we can do a quick graph of that by hand. Okay. Let's call this 1, 2, negative 2, 2. We'll go up 1, 2, 3, 4, 5, 6. And we know we always begin with x squared, our parent function. And that would have a point at 0, 0, 1, 1, negative 1, 1, negative 2, 4, positive 2, 4. We'd have that classic little parabola shape going on. But if we were to graph, let's graph our guy in red. This is f of x equals x squared. If we wanted to graph the function we're interested in, x squared plus 2, we would shift up 1, 2. We'd make a point. And we'd still make a point in the same places. So we'd go over 1, up 1, over 1, up 1. We'd go over 2, up 4. Up here at 6, and we go over 2 up here at 4. And we connect all of our points. And let's just take a look at an example point here. So we went from the point 2, 4 on our original to the point 2, 6 on our f of x equals x squared plus 2. And notice the difference in these coordinates. From our parent function, we went from the y value 4 and we shifted it up 2 to become 6. So we added 2 to our y value to get 6. And we did that. We added 2 to all of our y values for our red function here. Okay. Similarly, let's talk about the example g of x equals x cubed minus 1. Well, again, if we have that classic cubic function, x cubed, let's call this -1, let's call this 1, -1. Alright. We know it does that. If we wanted to move that downward 1, right, because it goes down 1, we can say that it's going to be x cubed shifted down, just down 1. Then when we graph g of x, we can start here at 1, and then we can make that little curvy shape still the same. So it would go up, it would curve, and it would go back up. Okay. This isn't the best graph, so let me just throw this in the calculator real quick to show you a little bit of a better example. Alright. So if we had, can we see that okay if I type something in? No, we can't really. Okay. So let's expose that a little bit more. There we go. Okay. So if we do our parent function, we know we had x cubed, so we do x cubed. And then we want to do our other function, the one we're going to do in red, so we're going to say x cubed, we're going to say minus 1. Here's what they would do. There we go, that's a little bit better. What you can see is happening here is that in red we have our blue graph just a little bit below, right? And it goes through -1. That's exactly what we wanted to show. Alright. Similarly, let's talk about the function h of x squared equals x plus 2 cubed plus 1. We understand that the parent function here is x cubed, and we can see that we have a plus 2 inside the parentheses. If we look back at what we just wrote, we know that that means it shifted to the left 2. We also have this plus 1 at the end, so it's going to go up 1. It's going to shift left 2 and it's going to go up 1. And let's look at our calculator to find that out. So we're still going to have, we're still going to have the parent function of x cubed, but now we're going to put in our functions. We're going to say x plus 2 cubed plus 1. And now when we graph both of these, let's see if we were right. There's our blue, our original parent function. And here's our red function, and we can see our function, our h of x, did in fact move to the left 3, and it moved up just 1. Let me fix my window so we can see that just a little bit better. If we go over here, let's go by 8 and -8. Let's try that. There we go. There's our f of x. And now we can see that our h of x does in fact go over to the left 3 and up 1. Let's do another example. And we're just going to start listing, not keep on proving graphically. So if we had f of x equals x minus 4 squared. It's important that we recognize our parent function is x squared here, and then we have that minus 4 inside. Oh, let me fix. There we go. It's a little bit better. We have that minus 4 inside, which means that this would be shifted to the right by 4 units. If we had the function g of x equals x plus 1 squared, well, check it out. We know we have our original parent function x squared, so this would be that parabola x squared shifted to the left this time 1. If we had the function g of x equals x plus 4 squared minus 2, again we can see that our parent function is x squared. So we say x squared shifted. This would be to the left again, to the left 4. And then we have that minus 2 at the end, which means it would go down 2. Alright. Let's talk about reflections. So, good rule of thumb. We have a reflection over the x-axis if our function is a negative of our parent function, and we have a reflection over the y-axis if our function is f of negative x. Not a whole negative function, but the value inside the parentheses is negative. Alright, so let's take a look at different kinds of examples. So say that we had the example, consider the function and its graph f of x equals x to the 4th, and we have that kind of funny looking graph. Here we would have 1, here we would have negative 1. Let's go up 1, 2, 3, and here's what happens. When we come down, we get kind of flat, right? It touches at 0, 0, but it gets kind of flat there, and then it goes and it curves back up. That's the graph of x to the 4th. And now let's consider two other functions. Let's find the equation for the graphs of g of x and h of x. So, considering this is what x to the 4th looks like, if we had then functions that did this. So, here's our graph. Here is 1, here is negative 1, and here we have 1, 2. And our graph was doing the following. It gets kind of flat up here at 2, and then curves, and does the same thing on the other side. And we call this one g of x. And then over here for f of x, what we have going on is the following. We'll call this one 1, 2, 3, 4, 5, and we'll go down 1 to negative 3. The graph of h of x looks like this. It touches right here at 4, and then starts to do that curvy thing. Gets flat at 4, and then starts to do that curvy thing. Again, this is h of x. Let's talk about what we see is happening. We know that x to the 4th by itself looks like this, and it looks like to get from x to the 4th to g of x, we did a few things. The first thing we can see is that we reflected x to the fourth over the x-axis. And we can tell that because now it's facing down instead of up. We can also tell that this shifted up 2 units. It's no longer touching at the origin, it's touching at y equals 2. So we can say shifted up 2. And now what we can do is take this information and write an equation for g of x. So we can say g of x equals, and we're going to say something important, negative x to the fourth. That is how we show reflection over the x-axis. We make our parent function negative out front. And then we want to say it shifted up 2, so we're going to say plus 2. Over here, for h of x, we can also tell that this one was reflected over the x-axis as well, because again, it went from an upwards facing function to a downward facing function. So that means that it reflected over the x-axis. And it didn't go up or down, it's still touching on the x-axis, but it does go over, it looks like 1, 2, 3, 4. So we can say it shifted to the right 4 units. And when we combine all this information, we get h of x equals, again, negative x to the fourth because it reflected over the x-axis. And, oh, hang on. I started this off incorrectly. Let me begin again here. We're going to have a negative, but then remember, since it shifted out to the right 4 units, that means that we say x minus 4 to the fourth. If it goes left or right, you have to include that inside the parentheses. So h of x equals negative x minus 4 to the fourth. Alright, so let's talk about stretching or shrinking. Stretch or shrink. Alright, so we have 2 cases of this. We either have a vertical stretch or shrink or a horizontal. And here's how you can tell the difference. Vertical means that you have a constant, a c value, out front of your f of x. And a horizontal means that you have a c value inside the parentheses next to your x. And some important things for you to understand is that when your c value for the vertical, when it's outside, when c is greater than 1, you have what's called a stretch. And on the graph, that looks like your graph is getting thinner. When c is between 0 and 1, we have what's called a shrink. And that means that your graph gets wider. For horizontal, when c is greater than 1, you have the opposite. You have a shrink, which means your graph looks like it's getting thinner. And then when c is between 0 and 1, you have a stretch, which makes it look like your graph is getting wider. Okay, so let's do some examples of this. Let's see, compare the graph of each function with the graph of f of x equals absolute value of x. Remember, absolute value of x is one of those key graphs that we talked about in our last video that we should generally understand what it looks like. Remember, it's that classic V shape. So let's compare, first of all, let's call this one part A. The graph of h of x equals 3 times the absolute value of x. So given our parent function is absolute value of x, we can tell that our c right here is 3. That's our c value. We can see that c is greater than 0. So what we have going on is a vertical stretch. And again, just so we understand what we're looking out for, that means we know our graph is going to look thinner. And what we can do here is just look at a table of values first of all, and then we'll graph. So for f of x, for every x and y value that we substitute in for just the absolute value of x, we get the same y value. So we would get 1, 2, and 3. If we input that, our output would also be 1, 2, and 3. That's how absolute values work. However, for h of x, we could have the same inputs of 1, 2, and 3, but now they're going to be multiplied by a factor of 3. So we would have 1, and the absolute value of 1 would be 1. 1 times 3 would be 3. We could put in 2. Absolute value of 2 is 2. 2 times 3 would be 6. And put in 3, we would have absolute value of 3, which would be 3. And 3 times 3 would get us 9. And we can see the relationship between these two. Let's do a little bracket. We can see that our y values for h of x were multiplied by a factor of 3. Oops, can we see that okay? There we go. It looks like our y values for h of x were multiplied by a factor of 3. And here's what that looks like on our graph. Alright, so if we have points 1, 2, let's call this 3, 1, 2, 3, and we have 1, 2, 3, 4, 5, maybe 6 right here at the top. Let's call this guy 5. We know for our classic f of x, we have 1 at 1, 1, 2, 2, 3, 3. Oh, let me do it a little bit better. 3, 3. We'd have one up here at 4, 4, and so on, right? It would just make that classic, really nice looking V shape. And up here at 4, 4, definitely, okay. That's what our f of x would be doing. And we'll label this guy our f of x. And now our h of x, if we use these points to help us out, when x equals 1, y now actually equals 3, and vice versa, right? Remember, again, getting used to how these classic functions work, absolute value reflects over the y-axis, so I only need to know one side of points, and then I can just reflect them over. So if I know that there's a point at 2, 6, for example, that means there's a point also at negative 2, 6. Use those reflections to help make this process a little bit easier. Alright, and there we have h of x, and it has vertically stretched by a factor of 3. If we have g of x equal to 1/3, we'll call this one part B. G of x equals 1/3 times the absolute value of x. Again, since our parent function in this case was absolute value of x, we know that our c is 1/3. We know c now is between 0 and 1, so we have a vertical, am I right to say shrink? I am. We have a vertical shrink. And what we can see by looking at a table here, so we have an x and a y of our f of x, and we had the values, let's say, 3, 6, and 9. Our y values would also be 3, 6, and 9. That's the nature of absolute value. However, if we're looking at g of x, this function that we're interested in, that's no longer the case, because now we're multiplying all of our y values by 1/3. So if we substituted in the 3, the 6, the 9, our y values would now become 1, 2, and 3. And again, the relationship that's happening here is that y values are shrinking by a factor of 1/3. And so, what this looks like in our graph, let's see if we can get some high values going. Okay. So if we had, let's say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we had 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's give ourselves some reference, so like 3 and 3. Cool. Our f of x, again, would just be doing that classic move up 3 over 3, 4 and 4, 5 and 5, right? It just keeps doing that. 3, 3, 4, 4 is a point, 5, 5 is a point, and it just looks like that classic V shape, kind of like at a 90-degree angle at the origin. But our h of x, or pardon me, our g of x now, like we talked about, is different. Now, when x equals 3, we don't have 3, we actually have 1. Now, when x equals 6, all the way out here at 6, we have a y value of 2. And vice versa, because I can reflect this over the y-axis. And out here at 6, I have a y value again of 2. Oh, should be a little bit higher. There we go. And now I can connect my points. Alright, and we can see that these two graphs do look very, very different. Here's our g of x, and here's our f of x. And it looks like when we multiply on the outside by a fraction, our graph gets wider. Alright, let's talk about horizontal stretches and shrinks now. So, if we're asked to compare the graph of each function with the graph of f of x equals 2 minus x cubed, and the first thing we're tasked with is to find when g of x equals f of 2x. Immediately what we can tell is going on here is a horizontal, this is our c value right there next to the x, and we can tell that we have that horizontal shrink. Horizontal shrink, which is going to mean that our graph looks thinner. And what we need to do here in order to find the equation of g of x is find what f of 2x equals. So we can substitute in 2x for every x value in our original function. That means we'd have 2 minus 2x cubed, which would be the same as saying 2 minus 8x cubed. And let's use our calculators to make this one a little bit quicker. Alright, so we're going to substitute in, there we go, okay. And if I expose this a little bit better, there we go, much better. If we substitute in for the blue for the top one our 2 minus x cubed, and then below we fill in for g of x, which is 2 minus 8x cubed. We can graph those at the same time to see what's happening here. There's our blue, our original, which is x cubed. And here we can see our red. And it did in fact get thinner. That's what's important to realize there. And there's another note I'd like you to write below here. It's important for us to realize that our y values, let's draw a little arrow out from our horizontal note. Or pardon me, we're talking about our x values now. Our x values are multiplied by a factor of 1/2. That is what happened from our f of x to our g of x equation. Oh, there we go. Let's do one more. So say that we had, oh, not a new example. We're just doing part B now. So part B would say g of x now equals f of 1/2 of x. And what we can say about that is that our c value is between 0 and 1. So now what we have is a horizontal stretch. We know our graph is going to get wider. And just like up here, when x values were multiplied by 1/2 when we substitute in 2x, now when we substitute in 1/2, our x values are multiplied by a factor of 2. And we're going to graph this and we're going to look at the table to really understand what that means. So, back to our calculator here. Help if we can see it. There we go. Okay, so now we go back to our y equals. We still have our original f of x in there, 2 minus x cubed. But now, what we need to put in there, first we need to find it, so let's make sure we do that. What we need to put in there is our equation for g of x now. If we were to substitute in 1/2 for every x up here, what we would get would be 2 minus 1/2 x cubed, or we'd get 2 minus 1/8 x cubed. Now we know what our next function is going to be. Let's substitute that in. We've still got 2 minus, but now we're going to insert a fraction, so alpha y equals 1/8, and then we do x cubed, and now we graph them. Let's see if we were right. Let's see if our red function is going to get wider. And there we have it. It does in fact look like our red function sort of horizontally stretched our graph. Let's look at our table. So let's press second graph. Let's take a look at what happened here. So here's our f of x values. Here's our g of x values. And here's what's interesting. Before, we had a y value at 1 when x equaled 1. But now for g of x, we don't have a y value of 1 until x equals 2. So we had to multiply our x value by 2 to get a y value of 1. When we had a y value of -6 for our f of x, for our g of x, we don't have a y value of -6 until we have a 4. So what used to happen at 2 now doesn't happen until 4. That's how we describe our x values being multiplied by a factor of 2. Alright, that is all I have to show you. We'll see you in class. Thanks for watching.